Alright, so today we're going to focus on points, lines, and planes. And today is the easy part of points, lines, and planes. When we get into parallel lines and transversals, it'll get a little bit more difficult. However, you do have some additional writing I want you to put in here. So you had some review. So I want you to go ahead and decide 1, 2, or 3, 1, 2, and 3, which one of these belong to those nets. So you got about 15 seconds. Alright, so there's your answers for those 3. And I put over here to the side what the solids are called because I want you to get used to that. I know that this is a square pyramid because if you look at the one face on this net that's different from all of the others, there's 5 faces on this net. The one that's different is the square. It appears to be a square. And so that's its base. And so it's called a square pyramid. Pyramids and prisms. Pyramids have 1 base, prisms have 2, and the bases on the prism are parallel to each other, so you don't have this point, this sharp point that could be used as a weapon. They're always named by their bases. And so this one, for number 3, this is the net, this is a rectangular prism. I guess technically, well, we would never call this a square prism, even though out of the 6 sides here, the 2 that are different are these ones. Technically, those are the bases. This one's unusual to be called a rectangular prism. But all prisms have rectangles going around the bases, and then the 2 faces that are different are those bases. So these could have been triangles, and it'd be a triangular prism. They could be a hexagon, and they'd be a hexagonal prism. But your net would look exactly the same. But those bases will change. And then your cylinder, typically your cylinder, and I have for you a lovely little example. So if you got this cylinder, the bases are circles, right? And your cylinder could be sitting this way. It does not have to be sitting on its base. But if I take that label, so if you consider it a canned good of some sort, if I take that label and cut it vertically right through there and unpeel that label, doesn't the label turn out to be a rectangle? So all cylinder nets will have a rectangle as part of their net. That's going to be called your lateral area, which we'll get to more in detail later. And then your circles for the bases, you just have to have 1 on each side. It doesn't matter where you put them, just 1 on each side. You don't want them on the same side because then they'll overlap. All right, so then we have some vocabulary for today. We're going to start in this chapter to use conjectures and hypotheses and conclusions in order to start our process of proofs. And so, highlight the following. A conjecture is a guess or a prediction. You're going to look at a situation and make a guess about it. I might look at your face this morning and decide whether you're in a good mood or a bad mood. That's a conjecture on my part. It could be correct, it could be wrong. The actual definition of a conjecture is that it is reached by using what's called inductive reasoning. Now, a true conjecture, you gather your facts, and based upon your facts, you're going to make this conjecture, this guess. So it is based upon facts. So perhaps if I looked at your face, I might actually start asking you questions. Did you get some sleep last night? Did you eat a good breakfast? Did you have a fight with mom or dad? Then I might be able to determine whether you're in a good mood today or not. So sometimes your conjecture can be a verb, sometimes it can be a noun. So if you make a conjecture that your volleyball team will win, is that a verb or a noun? It is a noun. Make is your verb. So you're making a conjecture. That's your noun. What did you make? A conjecture. It's like if you made a cake. The cake would definitely be a noun. Number 5, assuming that your sister ate the last cookie is a conjecture. So assuming is the conjecture. Assuming is what? A verb. So if assuming is the same as your conjecture, what is conjecture in this sentence? Assuming that your sister ate the last cookie. Oh, wait. Assuming that your sister ate the last cookie is a conjecture. That is a noun, isn't it? Look at the difference between these two. You conjecture, isn't that your verb now? Yep. So this is your noun. And this one would be your verb. Typically your conjecture is going to be a noun. But the way they've written in number 6, it becomes a verb. Alright, so flip it. Turn it. On this page, we're going to do a lot of additional writing. We don't have enough of a definition for each of these terms. I wouldn't stress about whether a term is defined or undefined. These are all definitions, and every one of these you want to make flashcards for. So you might want to write yourself a note. All of these should be on flashcards. So these are your first set of flashcards. You might want to add something yesterday if you don't remember what orthographic is or isometric. So this first thing that we have here, they've got a picture and they have their proper notation. Your notation is huge in geometry. If you use the wrong notation, you are going to get the answer wrong. So this right here is huge. You must know the notation. So when you make your flashcard, make sure that you put both the picture of what it is and the proper notation. So this is just a point. A point is just a dot. Proper notation for a point is just a capital letter. If you see a capital letter, your assumption is that they're referring to a point. They don't have to say point A, but oftentimes they will say point A. And so the proper definition for a point is a location. Write small. A location with no size. Points really have no depth, width, or height. They're just a location in space. They have no size. It's really not even a dimension. You can see a point if you make it big enough. But if you make it so small you can't see it, how do you prove that there's a dimension inside it? All right, then the next one, this right here is a line. A line has at least 2 points and it extends in 2 different directions. The proper notation for a line would be any 2 points that are on that line. And in this case, you're only showing A and B. But if I had, like, way down here, I've got A, C, and B, I could have named this line right here line AC, line CB, or line AB. And I can also flip those letters as well. You only name a line with 2 points, and then you put a little line with arrows on both ends above it. If you put only an arrow on one end, you're naming this thing down here, which I'll tell you what it is in a minute. So a line contains at least 2 points and extends, you can use a little and symbol, and extends in 2, and it must be opposite directions. Otherwise, you create an angle. Infinitely. A line has no thickness. You can just see it. So a line is really just one-dimensional. It's like perimeter in a classroom, or perimeter in a room, or perimeter of a fence. That also is one-dimensional. You can see perimeter, but the minute you touch the perimeter, if I touch the perimeter of this room down there, I'm really touching the floor and the wall. I can't really touch perimeter, but I can see it. So lines have no depth. This next thing is a plane, P-L-A-N-E. Now, it appears that the notation for a point in a plane are the same, bold the capital letter. Oftentimes you will see, and this textbook doesn't do it, but I'm used to points being named with lowercase letters, to be perfectly honest, because typically we name planes with uppercase letters. But notice that on this picture of the plane, and the plane extends in north, south, east, west infinitely. So this is just a snapshot of a plane. This paper is a snapshot of a plane. The wall is a snapshot of a plane. Your desk is a snapshot of a plane because it's an infinite thing. If we take a three-dimensional figure, like the sugar cubes from yesterday, they are made up of 6 different planes that intersected to create that sugar cube. Each one of the faces on that sugar cube is just a snapshot of the plane that contains that polygon, which in this case is a square. So a plane is a flat surface extending in all directions infinitely. So to name a plane, they've named the plane here just plane P. But a plane is named with any 3 points that are not on the same line. Because if you name a plane with 3 points that are on the same line, you're only defining the line, not the plane. Because we've got to give that plane some depth and some width. And so here, some additional names for this plane could be ABC. You cannot name a plane with more than 3 letters, and you cannot name a plane with less than 3 letters. Unless it's, in this case it's P, it technically should be a cursive P, but again this textbook doesn't show it that way. And P in this picture doesn't have a point associated with it because they're calling that plane P. I could have also rearranged these letters to be VAC, CAV, and there's 3 other forms of it. But these are just 3 examples. There's 6 altogether that I could have arranged these 3 letters. Then this is called a line segment. A line segment is part of a line. And it will contain 2 points. Now, a line segment, you cannot name any way that you want to, like you could this line here. Because this line here is infinite in both directions. It doesn't have a real beginning or an end because you can't really measure the length of that line because it never ends. Whereas a line segment, we can actually measure its length. So it has a definite beginning and a definite end. So this line segment can be named AB, and notice that it's got a line segment above it, no arrows on it. You could also have named it BA, also with a line segment above it. Either one of those are acceptable. It's the same name for the same segment. And so your true definition for a line segment is part of a line containing 2 endpoints and all points in between. A line contains an infinite number of line segments. A line contains an infinite number of points. And they'll never say this, but technically a line segment could contain an infinite number of points as well, because a point has no size. So I can put an infinite number of no size items within here, but they'll never say that. This right here is called a ray. Notice that its notation, an array is very particular. So on the line segment, I could name that line segment AB or BA. But on the ray, this is the only name for that ray. Well, in this particular diagram, you can name this ray AB because there's only 2 points on this line segment, so to speak. The beginning of that ray is at A, although your textbook will call it an endpoint. To me, it's really a start. And it goes through the point B. And it goes infinitely in the direction through the point B. So you have to start that first point with its starting point here, A. If you name this ray BA, then that ray actually goes in this direction starting from B, and it goes infinitely to the left through A. That's a totally different ray. It's not the same ray, so be really careful with your notation for rays. So the definition for ray is part of a line that has one endpoint and extends in one direction. And then the final one at the bottom is called opposite rays. It looks like a line. The only difference between these two is it has 3 points on this one and this one has 2. If I were you, you can usually call this a line as well because technically it is. And you'll see in the definition that part of the definition is that opposite rays are a line, because they form a line. If you were to take your highlighter and you had 2 different highlighters, they've got 2 different rays noted here, ray CA and ray CV. So ray CA starts at C and goes through the point B. So it's going in that direction through the point B. So this would be ray CV. Oh, I totally underlined the wrong one, didn't I? Okay, so yeah, there's ray CV. I'll fix it. Maybe. Hold that one. Okay. Then ray CA goes in the opposite direction from C through A. And so that's your ray CA. Now we could have also named a ray going from A through B, and so you would have ray AB. So it would go from A all the way through B. That's another ray on that line, different from the other 2. So you could have had ray AB. Notice it doesn't matter what direction the ray goes, the arrow is always to the right. So the arrow above on the notation, it doesn't go right or left, it always goes to the right. You could have also named what other ray here? BA. Totally different ray. So BA would go from B through A. Did I miss any? I think that's all of them, right? All right, so your true definition for a ray, or I'm sorry, opposite rays, would be two rays that share the same endpoint So notice here that both of these rays share the endpoint of C. One goes in the direction of B, one goes in the direction of A. They share the same endpoint and form a line. If they didn't form a line, they would have formed an angle. And technically, a line is an angle. It's just called a straight angle. Then there's some additional vocabulary I want you to write off to the right side. So one of the things we're going to talk about is called collinear points. Co meaning with, linear meaning line. So it implies by using your Latin that they are points on the same line, and that's exactly what collinear means. So points that lie on the same line. So in this last example, A, B, and C are collinear points. If you look at the plane over here, are A, B, and C collinear points in that plane? No, you cannot form one line that contains all 3 points. So they are non-collinear. So that's our next definition. Well, we're not going to write that down. Let's just assume that it's non-collinear. It means that they're not on the same line. Let's go ahead and look at the definition coplanar. What do you think that means? Co meaning with, planar meaning what? Plane. So things that are in the same plane. So things that can be in the same plane are points, lines, typically. So if you've got lines that are in the same plane, they're coplanar. Now if I have 2 lines that are like this, they're coplanar. 2 lines like this, they're coplanar. 2 lines like this, they're coplanar. But the minute I do this, even if it touches the other line, can I, well, technically I could make these coplanar, couldn't I? But are they coplanar to this paper? Yes or no? This paper does not contain both of them. This goes through that paper, okay, but it doesn't contain both of them. What about this? Now, these I said that they could be coplanar because I could put a paper right through these, correct? And I could contain both of them because they're touching each other. But the minute I move them apart from each other, now can I put a paper through both of them? No. So these would definitely be non-coplanar. So coplanar just means points and lines that lie in the same plane. And then the last one is space. The final frontier. Your parents will appreciate that. So space just means everything that we exist in is space. And so space is a set of all points in 3 dimensions. So I'm just going to put 3D there. So let's start to go through some of these problems now that we have these, and we'll look at our postulates in a minute. But if I want to find the intersection of, what does that notation mean? Line segment AB, which is contained in line AB, by the way, and line Z. So find your segment AB. So here's AB, right there. And then line Z is right here. So here's AB, and here's line Z. what is their intersection? Two lines intersect at a point, don't they? And isn't that point A? So your intersection of segment AB and line Z is a point A. That's one of the things that you're going to learn, and that becomes a postulate, is that, oh, when two lines intersect, that intersection is a point. The next one is, what is plane AEH? So look at plane AEH, so find A, E, and H. Isn't that this side right here? Aren't there 4 points in that plane? So you could name this plane with 3 of those 4 points. So AEH is only one name. So you're looking for another one that contains D, A, E, or H. What would be another name? Because you've got these two, right? But this one has a G in it, which isn't on this plane, correct? So it would have to be this one here. Then what is the line that goes through points F and E? Well, you don't see line FE here, so find F and E. Here's E, and here's F. Those are the only 2 points that they state are on that line, but what else is that line called? So here's a new notation that wasn't noted up here. A line can also be noted, and notice here that they have a cursive L. Whoops, you can't see that. Notice here they have a cursive L. So you could have named that line also a cursive L. Lines are always named with a cursive lowercase letter. So that's what they've done here. That Y is not a point. It's referring to that line FE. So a line through F and E is line 1. Think about this, the intersection of 2 planes. If I take this paper and this paper, oops, there's answers, and I make them touch, what would you describe that intersection as being geometrically? Is that a point? All the way through here, is that a point? No, look at the wall over there. That wall and that wall. See how they intersect over there? What would you call that thing? That intersection? A what? A line. So when 2 planes intersect, you should be looking for a line. So we have the intersection of plane ABF. So I'm looking for A, B, and F. So here's A, B, and F. So that's this back plane right here. And I'm looking for C, G, and F. C, G, and F. So isn't this the side plane here? So this back, or this back right here, and this side plane. What do they have in common? Yeah, they have this right here in common, don't they? And so that can be named, in this case, it's going to be named as a line segment, isn't it? Because there's not a total line going through it. So here's that line segment notation. Line segment BF. And that means that the last one left must relate to the last question. It says the plane containing points E, F, and G. So here's E, here's F, and here's G. So isn't that the bottom? It also contains what point? H, and so that's why they've included H here. And so that's just another name for that plane. Just because they use 3 letters doesn't mean you can't use 3 different letters. So when you go to look at the answers in the back of your book, they may not put all the choices there. They may just put one choice there. You've got to know that yours is also acceptable. So then, these are your postulates based upon what we just did. And your definition of a postulate is right here, an accepted statement of fact. So we just looked at some things above, and we're going to make a conjecture based upon what we just learned. And so these conjectures are an accepted statement of fact. They become postulates. They're not proven. That would be a theorem. But they're accepted as a statement of fact because we could prove it if we had to. So first postulate, these are all flashcards. You want to put these on flashcards, and if I were you, I would put them in what's called if-then form. If this, then that, and we'll work on that later. But I would put on the front of my flashcard through any 2 points, put a slash there. That would be the front. There's exactly one, through any 2 points, there's exactly one, what? 2 points make a what? A line. So through any 2 points, there's exactly one line. So this would be the front of your flashcard, this should be the back of your flashcard, so that you could read them forwards and backwards. There's exactly one line through any 2 points. You ought to be able to read them forwards and backwards. So then look at the second one. Find the subject of the sentence. If, well, this one is actually an if-then. If 2 distinct lines intersect, so that's your if part, put a slash there, that should be the front of your flashcard. So if 2 distinct lines intersect, and 2 lines intersect, what do you get? A point. Then they intersect in exactly one point. So this is point. Postulate 1-3, and you may not name the postulates by their numbers here because different textbooks number them differently. I want you to know what the postulate says, not what this number is. If you put as a reason postulate 1-3, I'm going to mark it wrong. You have to use the words. All right, so if 2 distinct planes intersect, so what do we say about 2 planes intersecting? 2 planes intersect, what do you get? A line, right? So here's your front of your flashcard, the if, the back is the then, they form one line. And the last postulate, through any 3, and this is important because remember a plane is defined by at least 3 non-collinear points. Because if I just had 3 collinear points like this one, you're only naming a line. But the minute I have 3 non-collinear points, and that actually wasn't part of your, you might want to note that here on the plane. Let's add that in here because that's an important part of the definition. It's a flat surface extending in all directions infinitely that contains at least 3 non-collinear points. So it contains at least 3 non-collinear points. That's the true definition of one. So through any 3 non-collinear points, isn't that the subject of the sentence? There's a slash there. That's the front of your flashcard. There's exactly one plane. Make sure your spelling is accurate. Common Core will most likely mark you wrong for that. All right, so make sure you put those on flashcards. You need to know them. If I give you the if, you've got to be able to finish the then. If I give you the then part, the second part, you've got to be able to finish it with the first part. So you have to read them forward and backwards. I personally don't care if you know whether this is a postulate or a definition. So I'm just going to give you these. A point indicates a location. It has no size. That is a definition, but they want you to use you because it's an undefined term. Through any 2 points, there's exactly one line. Wasn't that one of the postulates on the other side? So that's a postulate. A line is represented by a straight path that has no thickness and extends in 2 opposite directions without end. That's a definition. That's a you. If, anytime you have an if and a then, it's a loud scream out that that's a postulate. So if 2 distinct planes intersect, then they intersect in exactly one line. That's one of those postulates on the other side. Another if 2 distinct lines intersect, then they intersect in exactly one point. Another postulate. And then through any 3 non-collinear points, there's exactly one plane. That one you could say is a definition or a postulate, but they're going to say that it's a postulate because that is exactly the one that we had back here. But technically, that's also the definition. Which is another reason why I'm not going to be picky as to whether you know what it is. Who cares if it's a definition or a postulate? All right. So for this one, question 25, draw and label points E and F So put points E and F on this line. Here's E, and here's F. Here's where it would be handy to have two different colors of highlighters. Then they want you to draw ray EF in one color. So here's ray EF. Where would ray EF start at? E. So it'll start at E, and it's going to go in this direction with an arrow at the end. And then they want you to draw ray FE in another color. So where does that start at? F, and it goes through E in the opposite direction with an arrow at the end. Do those rays form opposite rays? That's really the ultimate question here. So let's go through what they're asking you. Do ray EF and FE share an endpoint? Yes or no? Do they share an endpoint? What's the endpoint of ray EF? Well, okay. What they call an endpoint, remember, I really call a starting point. They call it an endpoint with a point. But doesn't ray EF really start, or its endpoint is at E? And what about FE? Or does it start at F? So do they share the same endpoint? No, because their version of endpoint is our version of a starting point. So the answer to that is no. Do ray EF and ray FE form a line? Yes, they do. It's right there. Are ray EF and ray FE opposite rays? What is the definition of opposite rays? Look at it on the other side. So there are two parts to the definition of opposite rays. Part one is that they share what? An endpoint. And part two is that they form a line. They have one but not the other, right? So the answer is no, they are not opposite rays. Because, why? Right, so they are not, you need to use a complete sentence. They are not opposite rays because, in use notation, ray EF and ray FE do not share an endpoint. They form that line, but they don't share the endpoint. And so that is a typical question that you'll be asked on a test to test your knowledge of a definition. Now we're going to look at finding the intersection of two planes. So you've got a sugar cube right there, and they've labeled all the vertices for you. I want you to circle the points that are not on line BF. So here's line BF. We go all the way through here, right? Line segment BF is just part of that line. So is A on it? What do they want us to do? Circle the points that are on line BF. Oh, or in one of the two planes, right? Or in one of the two planes. What are our two planes? Yeah, this plane here and this plane here, right? So is A in that plane? Yes. How about B? Well, B's on the line, right? How about C? Yes? Yep, it's over here on this plane, right? How about D? No. How about E? Yes. How about F? Yes, it's on the line, right? How about G? It's in that plane. And how about H? No, it's over there. So just those 6. Then 31, circle another name for plane BFG. So here's B, here's F, and here's G. They define this side here. What point is missing that we didn't use? C. So any one of these contains C. So would ABF be acceptable? A is not in that plane. Would BCD? D is not in that plane. How about BCG? VCG, that's acceptable, right? All three are in that plane. How about CDH? Yeah, D and H aren't even in there, right? How about FGH? No H again, right? Name two planes that intersect in VF. So those are the planes we've been working with, right? Here are some possible choices, just to let you know. ABE, ABF, BFE, AFE. I've run out of room. Then the other plane would be this one over here, BCF, BFG, CBG, and CFG. Those are just some. There's lots more. There's 9 of them for each one that you could use. Then flip it to the back. So this one's kind of interesting. Use the figure below. Draw line LM, line segment LM, LN, and MN as dashed segments, and then shade the plane. And then while you're doing that, let me pull up the calendar because we are running out of time. So today's lesson is, or today's assignment is on page 16, and it's 9 through 25 odd. (27 through 51) and 53 through 57 odd. A lot of that's identification. It looks like a lot, but you're just identifying it. These are all. Yeah. So you still should be able to do your homework. We're just working on extra problems. So that should get you through today's assignment.